Kinetic theory of gases developed by Maxwell and Bourles and others, the 19th century. It explains the behavior of gases based on the idea that the gas consists of rapidly moving atoms or molecules. It gives molecular interpretation of pressure and temperature of a gas and is consistent with gas laws and Avogadro's hypothesis. It correctly explains the specific heat capacity of many gases. It also relates measurable properties of gases such as viscosity, conduction, and diffusion with molecular parameters, yielding estimates of molecular size and masses. Behavior of gases for a ideal gas of a given mass. Boyle's law. V proportional to 1 by P when T is constant. Here V is volume, P is pressure, and T is temperature. Charles' law. V proportional to T when P is constant. This implies V proportional to T by P. This implies PV proportional to T, or PV equals to K cap K into T, where cap K is a constant which depends upon the number of molecules in the sample. That is K proportional to cap N, where cap N is the number of molecules in the sample. K is a constant, and this implies K equals to KV into cap K equals to KV into cap N, where Kv is a constant called Boltzmann constant and is same for all gases. From 1 and 2, Pv equals to Kv into Nt. This implies Pv by Nt equals to Kv equals to constant. Thus, we can write P1 V1 by N1 T1 equals to P2 V2 by N2 T2 for a given mass of gas. For a given mass of gas, there are two initial state and final state. For a given sample, number of molecules or atom remains same. So for a given sample N1 equals to N2, hence equation 3 becomes P1 V1 by T1 equals to P2 V2 by T2. That is PV by T equals to constant. Now for different gases, if pressure, volume and temperature for both gas is same, then P1 V1 by N1 T1 equals to P2 V2 by N2 T2 equals to Kv. This implies N1 equals to N2, that is both the gas contains same number of molecules at equal volume, pressure and temperature. If P1 V1 and T are same, PV and T, that is pressure, volume and temperature are same, then number of molecules N is also same for all gases, and this is Avogadro's hypothesis. Now again we have PV by NT equals to constant equals to Kv, where Kv is the Boltzmann constant. So we can write this implies P by N by V equals to Kv into T. So this implies P by N equals to constant. If T is constant, it means if temperature is constant, then P by N is also constant. So we can write P1 by N1 equals to P2 by N2, and here N represents number density, that is number of molecules per unit volume. Next point, if pressure of two gases is also constant, then N1 equals to N2, that is number of molecules per unit volume is constant for different gases. If pressure and temperature at now Avogadro's number at a standard temperature, means 273 Kelvin, and a standard pressure means 1 atmospheric pressure. 22.4 liters of any gas contains 6.02 into 10 to the power 23 molecules. This number is known as Avogadro's number and is denoted by Na. Thus, Na equals to 6.02 into 10 to the power 23 molecules. The next point, we have PV equals to N into KV into T. Question. Now 1 mole equals to 6.02 into 10 to the power 23 molecules. Hence 1 molecule equals to 1 by 6.02 into 10 to the power 23 mole. Hence n molecules equals to n by Na mole, where Na is the number. This is called our Avogadro number, which value is 6.02 into 10 to the power 23, and n by Na is represented by mu, which is a number. Thus we can write n molecules equals to mu moles. Thus mu equals to n by Na, where mu represents number of moles and n represents total number of molecules, and Na is the Avogadro number. This implies mu into Na equals to n. Now from 1 n to 2 equals to mu into Na into K into T equals to mu into RT, where R represents Na into Kv, which is also a constant, and we have a unique formula Pv equals to mu RT, and it is called ideal gas equation, where R is a constant. It is called universal gas constant. Its value is 8.314 joule per mole per Kelvin, or 0.0821 liter atmospheric per mole per Kelvin. Again, mu equals to m by m naught, where m is the given mass and m naught is the molecular mass or molar mass. M is the mass of gas containing n molecules, and m0 is the molar mass. Molar mass means molecular mass. Again, Pv equals to mu RT. This implies Pv equals to m by m naught into RT, or this implies P equals to m by V into RT by m naught, or P equals to rho RT by m naught, where rho is the mass density of gas. This is another formula. Question: what is ideal gas? The gas satisfying the relation Pv equals to mu RT at all temperature and pressure is called an ideal gas. Why real gases behave like ideal at low temperature and high temperature, low pressure and high temperature? At low pressures or high temperatures, the molecules are far apart and molecular interactions are negligible. Without interaction, the gas behaves like an ideal well.